Hello, in today's video, I'll be solving questions on A-level chemical energetics from February-March 2019, paper 4-2. Question 1. A. State one natural and one man-made occurrence of oxides of nitrogen. One natural source of oxides of nitrogen is lightning. Another is volcanic eruptions. Lightning provides the activation energy for nitrogen and oxygen to react to give the oxides of nitrogen. The man-made source of oxides of nitrogen is fumes from combustion engines. Combustion engines like car engines, jet engines, and engines used in power stations. These engines release oxides of nitrogen because as the engines burn fuel under high temperature and pressure, nitrogen and oxygen take advantage of this high temperature and pressure to undergo reaction with each other to produce the oxides of nitrogen. B. Under conditions of high pressure and a catalyst, nitrogen monoxide NO forms two other oxides of nitrogen, dinitrogen monoxide N2O and dinitrogen trioxide N2O3. The unbalanced equation is given as this. The enthalpy change, standard enthalpy change associated with this equation is negative 195.2 kilojoules per mole, and the standard gas-free energy of this equation is negative 102.8 kilojoules per mole. I. Balance the equation above for the formation of N2O and N2O3 from NO. At the product side of this equation, we can see two nitrogens here and two nitrogens here, which means a total of 4 nitrogens at the product side. But at the reactant side, it's only 1 mole. So it means we can put 4 here so that we can balance nitrogen on both sides of the equation. The moment we put 4 at the reactant side, we can see that oxygen is 4 at the reactant side. And oxygen is also already 4 at the product side. And so it means we just have to put 1 and 1 here. II. State how the oxidation number of nitrogen changes during this reaction. So for this, we are supposed to state the oxidation number of nitrogen here and the oxidation number of nitrogen here. To calculate the oxidation number of nitrogen in NO, we have to add the oxidation number of both nitrogen and oxygen together and equate that to 0 because the charge on this NO is 0. So that will be N plus the oxidation number of oxygen in most of its compounds is negative 2. And this is equal to 0 because there is no charge on NO. And so it means our nitrogen is equal to plus 2. So we got that by moving the negative 2 across the equal to sign. So we went from plus 2 to the oxidation number of nitrogen in N2O. To calculate the oxidation number of nitrogen in N2O, there are 2 nitrogen atoms there. So you have 2N plus the oxidation number of oxygen is minus 2. And that is equal to 0 as there is no charge on this N2O. And so you get 2N minus 2 is equal to 0. And so it means our N is equal to plus 1. So we go from plus 2 to plus 1. For nitrogen in NO, we have already calculated the oxidation number as plus 2. The oxidation number of N2 of nitrogen in N2O3 can be calculated as 2N since there are 2 nitrogen atoms plus the oxidation number of oxygen is minus 2, but there are 3 atoms of oxygen, so times 3, and is equal to 0 because the charge on this is 0. So that will be 2N minus 6 is equal to 0. So 2N is equal to plus 6 by moving the minus 6 across the equal to sign. We divide through with 2, and so N is equal to plus 3. So we go from plus 2 to plus 3. I. Calculate the entropy change for the reaction at 298 Kelvin. Include the unit in your answer. So we use the equation standard gas-free energy is equal to standard enthalpy change minus temperature times change in entropy. Gas-free energy is given as negative 102.8 kilojoules per mole, and the standard enthalpy change is given as negative 195.2 kilojoules per mole minus the temperature is 298 Kelvin times the entropy change. We can move this value across the equal to sign to get negative 102.8 plus 195.2 is equal to negative 298 times the entropy change. So we divide through with negative 298, negative 298, and the entropy change is negative 0.310. For the unit of these two is kilojoules per mole, but we divided that with Kelvin, and so that will be per Kelvin. Ivy, state whether the sign of the entropy change calculated in III agrees with that predicted from your balanced equation in I. Explain your answer. We know that entropy change is equal to the sum of the entropy change of products minus the sum of entropy change of reactants. If you consider the balance equation from I above, we can see that the total moles of gas in the product is 2, and the total moles of gas in the reactant is 4. And so if you use this equation and do our subtraction, it means that our entropy change should give us a negative value. And we can see that in III, the entropy change value we calculated is negative. It means that our calculated entropy change value in III agrees with the prediction in the balanced equation from I. So we have to say that yes, it agrees, as there are more moles of gas at the reactant side than the product side. Question 2, C. The equation for the formation of the gaseous hydroxide ion is shown. Half H2 gas plus half O2 gas plus A minus giving OH minus gas. The enthalpy change is equal to enthalpy change of formation of the gaseous hydroxide ion. Use data in the table and from data booklets to calculate the enthalpy change of formation of the hydroxide ion. You might find it useful to construct a Born-Haber cycle. To construct the Born-Haber cycle, I'm going to put the magnesium hydroxide solid at the bottom. Now we have Mg solid plus X. I am going to use variables X, Y, Z to show the conversions involved in the formation of the hydroxide ion. So from here to here, that's the enthalpy change of formation of the magnesium hydroxide solid. Then I can convert or atomize the magnesium solid to Mg gas plus Y, and this is the enthalpy change of atomization of magnesium. Once I have atomized magnesium, I can now ionize it. So I'll convert it from Mg gas to Mg plus A minus. The Mg plus in the gaseous state plus Z. And this is the ionization energy 1 of magnesium. Then I can also take it to ionization energy 2. So that will be Mg2 plus, then plus the 2OH minus gaseous, and this ionization energy 2. So from here we can move to the bottom, and once we are combining, so at this point we have formed the 2 moles of the hydroxide ion, and once we combine the Mg2 plus and the 2 moles of the gaseous hydroxide ion, that is lattice energy, so delta H lat. Now notice that X plus Y plus Z is actually equal to 2 times the enthalpy change of formation of the hydroxide ion. So instead of X, Y, Z, I am going to be using this in my calculation. To write an equation from this Born-Haber cycle, we know that the enthalpy change, standard enthalpy change of formation, is equal to the sum of all the other enthalpy changes. And so that will be equal to the enthalpy change of atomization of magnesium plus ionization energy 1 plus ionization energy 2, all of magnesium, plus 2 times the enthalpy change of formation of the OH minus ion plus the lattice energy. Enthalpy change of formation has been given as negative 925 kilojoules per mole. The atomization energy of magnesium is 148 plus the ionization energy 1 of magnesium from the data booklet is 736 plus the ionization energy 2 of magnesium from the data booklet is 1450 kilojoules per mole, plus the lattice energy has also been given as negative 2993 plus 2 times the enthalpy change of formation of the hydroxide ion. So we get negative 925 kilojoules per mole is equal to negative 659 plus 2 times the standard enthalpy change of formation of the hydroxide ion. So negative 295, we move this across the equal to sign, we get plus 659 is equal to 2 times the enthalpy change of formation of the hydroxide ion. So we divide all through with 2, so it means that the enthalpy change of formation of the hydroxide ion is equal to negative 133 kilojoules per mole. Thank you for watching. Kindly subscribe to this channel. See you in the next tutorial.